This is part 4 of the series Circles, and we'll begin this part with the theorem equidistant chords theorem. The equidistant chords theorem says, in the same or congruent circles, two chords are congruent if and only if they are equidistant from the center. So that says, if AB is congruent to DC, then the length of the perpendicular segment from the chord to the center of each of those chords is going to be equal. So this segment is going to be equal to this. Also, it says that if the chords are equidistant, that is, if this segment equals this distance, then this chord must equal this chord. So we're going to prove this theorem, and we're going to prove the piece that says the two chords, if the two chords are congruent, then they're equidistant from the center. And so let's, without further ado, get on with that proof. The strategy for this proof is going to be, given that this is congruent to this, we're going to draw in some auxiliary radii here, and we're going to show that this triangle is congruent to this triangle, and therefore these two altitudes are going to be congruent as well by CPC-TC. So let's begin, and we will write down our given and draw in some auxiliary lines. So here I've drawn in AP, PB, PD, and PC. And since those are all radii, we can write that they're all congruent. Now that we were given AB is congruent to DC, and we know that this is congruent to this and this to this, we know that these two big triangles, triangle PBA and PDC, are congruent by side-side-side congruence. And now, because these two triangles are congruent, I know that any corresponding part of those two triangles are congruent, so PE is congruent to PF, and that's by CPC-TC. This theorem is a fairly basic theorem to prove, but let's now go ahead and put it into practice. In this problem, we're given that LN is congruent to QU. LN is this chord, QU is this chord. We're given that OP is 3x plus 2, so the distance from chord LN to the center is 3x plus 2, and PR 7x minus 6, so this distance is 7x minus 6, and the length of LN is 12, so this chord's length is 12. We are charged with finding the radius of the circle. Well, in this problem, it looks kind of complicated, and it's going to be using a group of theorems that we've just finished talking about. So let's get started here. I need to find the radius. So what I'm going to do is I'm going to go ahead and draw in this radius so that we can see what we're working with. And I'm given that this piece is 12. Well, notice that MT is a diameter, and that diameter is perpendicular to LN. Now, based on the theorems we've just talked about, we know that if a diameter is perpendicular to a chord, that diameter is the perpendicular bisector of the chord. So that means that these two pieces, this piece is 6, and this piece is 6. So that gets us part of the way. We know that OP is 3x plus 2, and PR is 7x minus 6. Well, we know that if two chords are congruent, which it says they are, then they have to be equidistant from the center. So we know that this segment must be congruent to this segment. So using that, we're going to find the value of x, because we can say that OP, this distance, is equal to PR, this distance. So 3x plus 2 equals 7x minus 6. Let's subtract 3 from both sides. 2 equals 4x minus 6. Let's go ahead and add the 6. 8 equals 4x. Divide by 4. 2 equals x. That means that each one of these segments, each one of these distances, is going to be given here. So let's just substitute this in here. 3 times 2 plus 2 gives us 6 plus 2, 8. So we know that this piece is 8. And we're only left with finding this guy. So this is the hypotenuse here. And if you look closely, this leg is 6, this leg is 8, and this must be a 3, 4, 5 Pythagorean triple. Because 3 times 2 is 6, 4 times 2 is 8, so this must be 5 times 2, which is 10. So we know that H equals 10, because it's part of a Pythagorean triple. Had we forgotten that fact, we could simply do 6 squared plus H squared equals H squared. Take the square root of both sides. We get 36 plus 64, and that's 100. We know the square root of 100 equals 10. So either way, we come out with the same value. The radius of the circle is 10. Now let's move on to the next topic. Now we're going to look at what happens when two chords intersect inside a circle and they have a common vertex on the circle. In this case, we create an angle. And this type of angle is called an inscribed angle. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So angle QPR is an inscribed angle. Angle PQR, an inscribed angle, and PRQ is another inscribed angle. This would be known as an inscribed polygon. An inscribed polygon obviously is a polygon whose vertices are on the circle. So, this creates a couple of new topics. The first one is the idea of an intercepted arc. An intercepted arc is an arc between two lines, rays, or segments of the circle. So here we have two segments that intercept the circle at points Q and R, and they intercept this arc, arc QR. Chord PR and chord RQ intercept arc PQ, and chord PQ and QR intercept arc PR. So these are intercepted arcs. These are inscribed angles. So we would say angle P intercepts arc QR. We can also say that segment QR, this chord, subtends this angle. So the subtending of an angle is if the points of a chord or arc lie on the sides of an inscribed angle, then the chord or arc subtends the angle. So again here QR, this chord subtends angle P, and arc QR subtends the same angle. So angle P intercepts the arc, and the arc subtends the angle. I know it can be a little confusing, but after using the terms enough, it should become fairly second nature. So let's go on and talk about the measure of inscribed angles. To find the measure of an inscribed angle, that's all we need to know is the measure of its intercepted arc. And the measure of an inscribed angle is 1/2 the measure of the intercepted arc. Now if you recall, the measure of a minor arc is the measure of the central angle that intercepts it, and so therefore the measure of an inscribed angle is going to be 1/2 the measure of the central angle that intercepts its arc. Now before we look at the proof of this theorem, I want to look at another very closely related theorem that is going to be used quite often. This is the inscribed angles of a circle theorem, and you can think of it as just an extension of the measure of an inscribed angle theorem. And it simply says, if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So you can see here that this angle, angle BAC, is intercepting arc BC, and angle BDC is intercepting the same arc. Well, if this angle is 1/2 this arc, and this angle is 1/2 this arc, then obviously this angle and this angle have to be the same angles. Now the tricky part of this theorem is it works in both directions. You can clearly see here that angle ABD is intercepting arc AD, and ACD is also intercepting arc AD, which means that angle ABD, or angle B here, is congruent to angle C, or angle ACD. So this angle is congruent to this, and this angle is congruent to this. That's the nature of this theorem. So let's go ahead and see if we can't prove the measure of an inscribed angle theorem and see how these theorems work. Now, to prove the measure of an inscribed angle theorem, there are actually three possible conditions that exist. The primary is when one of the chords is actually a diameter of the circle. And that's the first case that we're going to prove. The second case is when the center of the circle is in the interior of the inscribed angle. That is, this chord BC, C would be down here, where BC would be down here. So the center would be in the interior of this angle. The third case is where point C would be up here, and the center of the circle is outside the inscribed angle. So to get through these, the first thing we're going to do is prove this theorem. In order to do that, I'm going to set up a triangle inside here. So we're going to draw an auxiliary line and create a couple of angles in here so that we have some relationships to work with. Because we're proving that given angle ABC is an inscribed angle, that the measure of angle ABC, this angle, is 1/2 its intercepted arc. For convenience, I've set up several angles in here. This is angle 1, which is angle ABC. This is an exterior angle to this triangle, and it is the measure of that arc, and these two angles in here. So our first statement is going to be to relate these two angles to this exterior angle here. So we know that angle 4 is equal to angle 1 plus angle 2, and that's the exterior angle theorem. Now, for the sake of time, I'm going to take a few liberties with this proof, and we can see that because BP is congruent to PA, because they're both radii, the base angles theorem tells us that angle 1 is congruent to angle 2, and therefore we know that the measure of angle 1 equals the measure of angle 2. So we just went ahead and consolidated, and we said measure of angle 1 equals the measure of angle 2 because congruent radii, base angles theorem, and definition of congruent angles. Now we can go ahead and substitute this in here, and we have the measure of angle 4 equals 2 times the measure of angle 1. So here we have the measure of angle 1 equals 1/2 the measure of angle 4, and that's by the division property of equality, and the symmetric property of equality allowed us to swap sides. And now we know that the measure of angle 4 is the measure of arc AC, and that's ultimately what we need on this side. So we're going to go ahead and do that substitution based on the definition of a minor arc. And so here we have the measure of angle 1, which is just a surrogate for the measure of ABC, equals 1/2 the measure of arc AC. And that's our proof. In the next part, we're going to go through the proofs of the other two cases, and both of those cases use this case, the proof of this case, to prove their elements. So this was a necessary first step to prove the inscribed angle theorem using one of the chords as a diameter. And so I will talk to you in the next part.